Okay, everyone. So we are looking today at section 4.3, the solubility product constant, or KSP. So we've actually seen K, obviously, a bunch of times in chapter 2 and in chapter 3. K is our equilibrium constant. Okay, so it looks a little bit different. It's not KEQ, it's KSP. Now, what we're looking at here is equilibrium that is happening within a saturated solution. So actually at the beginning of chapter 4, we already looked at this dissociation equilibrium. So if you recall, once you have a saturated solution, remember I showed that little animation on the PHET interactives, where after you have a certain amount of solute in a solution, you eventually reach a maximum capacity of that, the ability of that salt to dissolve. So what ends up happening is you have clumps of that recrystallized salt at the bottom of your test tube or your beaker. So eventually you have the rate of dissociation being equal to the rate of recrystallization. So we have now what's called a solubility equilibrium. Okay, so remember this can only happen once you have a saturated solution. So in this case, right, we have lead 2 chloride, and obviously it's dissociating into lead ions and chlorine ions. So what's happening here is we can now create a K expression using this equilibrium. So just a reminder that when we're setting up a K expression, so K is set up no matter what type of equilibrium we're looking at, it's always the same, right? Products over reactants. So in this case, you have to also remember that your reactant is a solid crystal, right? It's like our crystal lattice ionic compound. So when you're setting up your products over reactants, you would not include your solid within your K expression. So notice down here, they're doing the K expression. We have our lead concentration, our chlorine, and of course we still consider the exponent on that concentration being the coefficient from your equilibrium process. So really, solids are not there. So it's almost as if it's over 1, right? But we don't include the, of course, the 1 portion when we're looking at this. So we now are going to call this a KSP. So the only reason why we're denoting this as being something different is just to be a little bit more specific in terms of, yes, this is an equilibrium constant, right? K is an equilibrium constant, but we're being more specific that this is for a solubility product constant, or think of it as a KEQ for solubility equilibrium. Okay, so let's take a look at some of the terminology that you are now going to start seeing. So you're going to see terms such as molar solubility, and of course we know molar concentration. Now, molar solubility and molar concentration is literally the same thing, okay? So the solubility of a substance in a saturated solution is the concentration of that solute in the standard saturated solution. So when the question is asking you, determine the molar solubility of something, that's the same thing as saying find the concentration, okay? For some reason, it becomes a big confusing thing, and I'm not sure why, but anytime you're asked to determine solubility, it's the same thing as saying find the concentration of that solute. So of course, we're going to do that by having our KSP expression help us out. So just the same way that we would use the K expression and ice tables in the past with other equilibriums, we're going to do that the same thing here. So the solubility product constant, or KSP, is the product of the ion concentrations in the saturated solution raised to the power of the coefficients. In other words, we already know this. We're going to set this up products over reactants, and we do not include the solids. So let's take a look at an example here. Let's say we had silver phosphate. Okay, we're going to do our dissociation equilibrium. So we have 3 silver ions, right? So when you dissociate, we take into account the number of each ion. And we have phosphate ions. So if we were to write out the KSP expression for this, we would have silver ions to the exponent 3 and phosphate ions to the exponent 1 over nothing, right? Or over 1, not nothing. So something to keep in mind, when you have dissociation of your ions, we can use the mole ratios here to help determine the concentrations as well. So for example, if I were to say, at equilibrium, we have 1 mole per liter of phosphate, technically this would be equal to like our X, and you'll see this later. We'll look at some ice table setups. Because we have 3 times the amount of silver as we do phosphate, we could then safely say, well, we're going to have a concentration here of 3 moles per liter, right? So this would be like 3x versus x. Yeah. So this is just another reminder of how to set this up, but I think you are pretty, especially after doing chapter 2, we should be pretty confident at looking at the setup of that at this point. Okay, so let's talk about how the different degrees of solubility can affect the concentration. So of course, if we have an increase in the solubility of a substance, that means that we have a higher amount of ions in that solvent, right? So the larger your, I should say, the more soluble something is, the increase in the concentration of our ions. And if you take a look, because our KSP is directly related to the concentration of ions, your KSP value is going to become larger. So very similar to how we saw our KEQ, if you have a very large K value, usually that's indicative of having a lot of product present. Well, in this case, the product are our ions. So of course, the higher your solubility, the more ions in solution, the higher your K value is going to be. If you have something that has very low solubility, you're going to have a smaller concentration of ions, and your K value will also be smaller. It's a direct result. Okay, so let's start taking a look at calculating some KSP values. So just starting off nice and simple here. So it says calculate the KSP for each of the following. So we have calcium carbonate. Okay, so I would always recommend that you start off by writing out your solubility equilibrium. They always look the same. It's the dissociation equation, right? So we have calcium ions and carbonate ions here, and it's a 1-to-1 ratio, right? So here, check out the terminology. The calcium carbonate has a solubility of this concentration. So what they are saying to us, essentially, is that this is the concentration of this compound, or this solute, once it is dissolved in solution. In other words, this is equal to our X. They're telling us that that is the amount that this would essentially dissociate into. So KSP in this case, if we were to set this up, would be equal to our calcium ions and our carbonate ions. Okay, so because this is a 1-to-1 ratio, really this is as if we were saying we have 6.1 times 10 to the negative 5 of each of these ions, right? So this is the amount of solubility for this compound, but because everything here is in a 1-to-1 ratio, this is the concentration we're going to plug in for both of our ions. So this calcium and this carbonate are the same value. So essentially KSP is going to end up being 6.1 times 10 to the negative 5 moles per liter times itself, or we can just square it, same thing. Right? Now, let's say, so obviously I'm sure we can all calculate this out. So 3.7 times 10 to the negative 9. And same thing, there's no units for KSP. Now, let's say this was not a 1-to-1 ratio. Let's say for every 1 calcium, I'm being hypothetical here, for every 1 calcium there was 2 carbonates. That would mean that the carbonate value would be double this term, right? Double our X. So maybe you would clarify if I, if we were to write this as an ICE table, maybe we can do that. Just to give us some space here. Okay. So if this were an ICE table, imagine, so first of all, this is a solid, so it doesn't really impact us, right? So initially, we start off with no product. Our change is always positive X because we start from nothing, right? So we're producing it. And then we're going to have X and X. So do you see what I mean? We're not subtracting from anything because we don't have any of those ions there initially. So whatever we produce, that is going to happen to be equal to X. But if this, again, this is like a hypothetical thing, obviously this doesn't match for this, but if this was 2, then you would have to double your solubility in order to get the concentration for that ion that you have twice as many of. Okay, now you don't have to write the ICE table in. If it helps you at the beginning, especially with the 0, 0 and showing the addition of your X's, if that helps you to visualize it because it's something you're comfortable doing from the other previous chapter, then please, by all means, go ahead and do that. But essentially, if it's a 1-to-1, it's your X. Whatever your coefficient is would then be your multiplier if it's not 1-to-1. So let's take a look at, here's an example of one that is not going to be 1-to-1. Just a little spoiler alert here. So we have manganese hydroxide, right? So let's write out our equilibrium. And we have 2 OH groups. Okay, so it's telling us that it has the solubility of 3.6 times 10 to the negative 5. So our KSP for this is going to be Mn positive 2 and then OH to the exponent 2. So the numbers we're going to plug into here, this is our Mn because it's a 1-to-1 ratio. But before we can plug it in for our hydroxide, we have to double it. Right? So this is essentially our X. So if we have X here, but this is really 2X. So even though we are also squaring it, I know that sometimes can be kind of like a conflicting thing, but imagine this is as if you're calculating 2X. So here, when we plug this in, your values will be 3.6 times 10 to the negative 5. And then this will be 7.2 approximately, 10 to the negative 5 squared. So our answer here we get is 1.9 times 10 to the negative 13. Okay. At any point in time, obviously, before I start doing the answers to these, I'm hoping you obviously understand. You can pause the video and then give it a try if you want to on your own, and then continue with watching this. To see the corrections. Okay, so this is a little bit different. I might actually press pause here and continue this on part 2. And the difference here is we're still dealing with, of course, an ionic compound. We have a solubility, which is still equal to our X. Okay, but in this case, it's grams per liter. Okay, so we're going to have to start incorporating the mole into this. Because remember, whenever you plug into your KSP, it has to be in units of concentrations of moles per liter. So let's check this out in part 2.